Hello students, welcome to All Force e-learning channel. This is Nageshwar Rao, physics faculty. In the last session, we have started one chapter, current electricity. This is session number 83. Let us briefly recollect what has been completed in the last session. In the last session, I gave you introduction about electricity part. Okay, what is electric current, and few applications related to electric current were discussed, and one expression for a drift velocity was also derived, isn't it? This is what we have completed in the last session. So let us just have a look at what equations we have seen in the last session. The first equation is this one. What is this? Instantaneous currents equation, isn't it? I is equal to limit delta tends to 0, delta q by delta t is equal to dq by dt. So this dq by dt gives us instantaneous current, isn't it? And the next we have seen this equation, but this equation comes under the category of applications part. Okay, if a current has flown through a conductor, if I wanted to find out how much a charge has flown through the conductor, I can use this equation to find out the charge in a time interval from starting from t1 seconds to t2 seconds. If there is a current flow, if I wanted to find out how much a charge has flown, I can find out using this equation. What is this? Q is equal to integral T1 to T2 I dt. And the next one is, if n particles were taken, each of charge q, and if they are flowing in a through a cross sectional area for a time t, then average current associated with that is given by this equation. I is equal to nq by t, isn't it? And later one more application was discussed. If a charge is revolving in circular path, let the charge be q, it is revolving in a circular path of radius r with a linear velocity v. In such cases, what is the equation for current associated with the flow of charge or with the motion of the charge? This can be written as like this: I is equal to q by t, where t is time period. Okay, and further you can modify that 1 by time period. Inverse of time period is nothing but frequency, so you can write this equation as fq, or you can replace f with omega by 2 pi. What is that omega? Angular velocity or angular frequency. And finally you can write that equation as vq by 2 pi r. That's what we have written yesterday. I is equal to vq by 2 pi r. That was our conclusion. So if any charge is revolving in the circular path, there will be some current associated with that. We can think about that current, and we can write one such kind of equation. I is equal to vq by 2 pi r. And the next one is this equation: I is equal to n1 plus n2 into E by T. So N1 charges were flowing in forward direction, and N2 charges were flowing along the same direction. So then net flow of the charge will be N1 plus N2 multiplied with their charge divided by T. Okay, so N2 is actually electrons, negatively charged particles, and N1 yesterday we have taken that N1 as positively charged particles. And the last equation that we have derived is drift velocity equation, and this is that equation. What is this? Vd is equal to E by m into tau. That is the equation, isn't it? Where small e is electron charge, capital E is electric field intensity, and m is mass of the charge, tau is relaxation time. Okay, so let us see what we can do further. I'll discuss few problems connected with these details, and then I will proceed further with some other discussion related to drift velocity. I'll be talking about mobility. I'll be talking about relation between current and drift velocity. These things are important. So let us just have a look at 2 or 3 problems first. Okay, children? Okay, students, now let us discuss 2 problems. Here I have taken one problem. See this one. One hydrogen atom is given, and it was said that electron moves in an orbit of radius 5 into 10 power minus 11 meters with a speed of 2.2 into 10 power 6 meter per second. Calculate the equivalent current. So we had already a discussion about applications of electric current. If a charge is revolving in circular path, we can talk about current associated with that flow. Okay, so here electron is revolving around the nucleus of hydrogen atom, and what we have to find out? We have to find out the equivalent current associated with the flow of charge or movement of electron in the circular orbit. Let us see how it can be calculated. We know that current associated with a charge q, if it is moving in circular path, it can be expressed as VE by 2 pi r. That's how it can be expressed. Okay, where E is what? Charge of the electron. In fact, general equation is VQ by 2 pi r. Since we are dealing with the motion of an electron in the circular arc bit, you can replace q with e. So let us find out. Already v speed is given. How much is speed? Speed is given as 5 into, that's radius. Better let us write the details separately. Radius r is a 5 into 10 power minus 11 meters, and speed v is 2.2 into 10 power 6 meters per second. So I is equal to v 2.2 into 10 power 6 into charge of the electron. See, don't think it is not given in the question. All of you are familiar with the charge of the electron. How much is that? 1.6 into 10 power minus 19 coulombs, right? So charge of the electron 1.6 into 10 power minus 19 coulombs divided by 2 into this pi. I am going to replace with 22 by 7 into what is the radius given? 5 into 10 power minus 11. Okay, so let us calculate this. What you will get here, you will get 0.1. This is 7 can be taken to the numerator. If it is taken to the numerator, it becomes 0.7, 0.1 into 7 into 1.6 into 10 power 6 into 10 power minus 11. How much is minus 19? How much is that? 10 power minus 13 divided by, and what do we have in the denominator? 2 5s are 10, 10 into 10 power minus 11, it's 10 power minus 10. So finally, what will be the answer? If you multiply these two things, 0.7 into 1.6, how much is that? It's 1.12 into 10 power minus 3 by 10 power minus 10, it is equal to 10 power minus 3 cool. Amperes. So how much is the current? I is equal to 1.1 into 10 power minus 3 amperes of current is associated with the whatever electron is revolving in the circular path around the nucleus. Or you can express this as I is equal to 1.12 into, this is what, 10 power minus 3 can be considered as milli, so milliamps. So this is the current associated with the revolving electron. Now let us have a look at this question as well. This is about, how much a charge has flown through a particular cross section if current data is given. If current is flowing, in the sense, what does it mean? Charge is flowing. So if current value is given to us, we can find out how much charge has flown, okay, when the so and so current has flown through the given cross sectional area. So let us find out. It was said that current through a wire depends on the time, as current is given as a function of time, I naught plus alpha t. I is equal to I naught plus alpha t, where I naught is 10 amperes and alpha is 4 ampere per second. Find the charge that crossed through a section of the wire in 10 seconds. So we have to find out how much charge has flown through the section of the wire in 10 seconds of time. See, alpha value is given as 4 ampere per second. Okay, so here he has tried to make sure that dimensionally this equation is correct. See, its dimensions are what? Its dimensional formula can be expressed as ampere, right? Current is a fundamental quantity. You can write it as a power 1, or simply you can write it as a. So here it is current. Here also alpha t. Finally, it should have dimensions of current, so that its units are taken as ampere per second. Okay, so dimensionally it is correct. So now let us find out how much a charge has crossed through a cross section of the wire in 10 seconds. What was the conclusion when we had a discussion about applications of electric current? The charge that has flown through a cross section can be calculated using this integral t1 to t2 I dt. Okay, so what is t1 here? You can here lower limit, upper limit, they were not defined. It was said that over a time of 10 seconds. So you can take t1 as 0, and the upper limit can be taken as 10 seconds. So within how many seconds of time you are finding the charge that has flown through a given cross section area? 10 seconds. Okay, and here I is what? I is equal to I naught plus alpha t into dt. Okay, so this can be written as, after integrating this, what you will get? I naught t plus alpha t square by 2. I hope all of you are familiar with the basic equation related to integration. What is that basic equation? Integral x power n dx can be written as x power n plus 1 by n plus 1. This is the equation. Okay, so using this equation, I naught can be written as I naught t plus, alpha t can be written as alpha t square by 2. So now let us apply these limits. If you replace t with the 10, what you will get? 10 I naught plus, and here 10 square, 100, 100 by 2, 50. So 50 alpha. When you replace t with 0 and here 0, the entire term vanishes. So no need to worry about whatever value you will get after substituting this 0 lower limit. So this is what q we are getting. Okay, but see, look at the question once. I naught and alpha values were given. So you can replace I naught with what? 10 amperes, and alpha can be replaced with 4. Let us replace. So 10 into I naught is what? 10 plus 50 into alpha is 4. Okay, so 100 plus 450 is 200. So 300 coulombs of charge has flown through a given cross section area. Okay, so that's how you are supposed to solve the problems. Okay, let us see. Let us try one more problem. Okay, students. Now let us discuss about these two problems also. The question number 3 is a current of 1.6 amperes is flowing in a conductor. The number of electrons flowing per second through the conductor is. What was said? A current 1.6 amperes of current is flowing through the conductor. We have to find out how many number of electrons are flowing per second through the conductor. It's quite easy. You can find out. See, we know that average current can be expressed as I is equal to nq by t, where n is the number of charged particles and q is charge of each particle divided by time. Here, what are the charged particles? Electrons are the charged particles, right? So, and I is given. How much is I? I is given as 1.6 amperes. We have to find out n, and q is what? It's electrons charge, isn't it? How much is that? 1.6 into 10 power minus 19 coulombs, and the t per second. He is asking about the number of electrons flowing per second. So t is equal to 1 second. So what we have to find out? N value. So n is equal to it from this equation. What you can write? It by q. I is how much? 1.6. Time is 1 second divided by q is 1.6 into 10 power minus 19 coulombs, isn't it? 1.6 gets cancelled. If this 10 power minus 19 is taken to the numerator, what you will get? 10 power 19. So how many electrons flow is associated with this current 1.6 amperes in 1 second of time? 10 power 19 electrons. Okay. Now let us have a look at this problem. If an electron revolves in the circular path of radius 0.5 angstroms at a frequency of 5 into 10 power 15 cycles per second, the equivalent electric current is. See, already we have solved one problem, based on such kind of model, hydrogen atom problem, isn't it? So there, what was given? Speed of the electron, revolving electron is given, and the radius of the orbit is given. Okay, so we have used VE is equal to 2 pi r equation, and we have calculated current associated with the revolving electron. Now its data is slightly different. See, whatever data it might be, we'll start with the basic equation. What is that basic equation? Average current associated with the flow can be written as Q by time period, isn't it? Charge divided by the total time taken for this charge to complete one revolution around the nucleus. Okay, so here Q is what? E. And what is this time period? See here, data related to frequency is given. 5 into 10 power 15 cycles per second, in the sense he has given frequency, right? 1 by t is nothing but frequency. So you can replace this 1 by t directly with frequency. So E into F. Okay, so therefore I is equal to, what is E? 1.6 into 10 power minus 19 coulombs, and frequency is how much? 5 into 10 power 15. So 5 16, how much it will be? 8. 5 into 1.6 is equal to 8 into 10 power minus 4 amperes, or you can write this as 0.8 milliamps. So how much is the current associated with that revolving electron? 0.8 milliamps. Okay, so now let us continue with discussion related to drift velocity. I'll discuss about mobility, and I'll discuss about relation between current and drift velocity. Okay, children. In the last class, we have derived this relation, drift velocity. So equation, what is that? V subscript d is equal to E tau by m. Of course, if it is in vector form, you will have a negative sign here. So what is this tau? Tau is relaxation time. Tau is, you can call this as relaxation time. Relaxation time in the sense of time taken by the electron between two successive collisions. That's where it is in rest position. Continuously it suffers collisions with the atomic sites, and between one collision and the other collision, it moves without any other collision, without any disturbance. Okay, such a kind of whatever time is associated with that journey between two consecutive collisions, that time is called as relaxation time. Even this is average value only. Yesterday you might have seen the derivation, tau 1, tau 2, tau 3, like that, up to tau n values were taken, they were averaged, and finally that is replaced with tau, tau 1 plus, tau 2 plus, and so on. Tau n by n is replaced with what? Tau, and this tau can be called as relaxation time. If you remember in kinetic theory of gases in first year, you were already told about this one, mean free path. Mean free path in the sense the average distance traveled by the particle between two consecutive collisions can be called as mean free path. And if you want, you can express that mean free path also. Here Vd is average value only, tau is average value only, mean free path is also average value only, isn't it? Why do we go for averages? Children, remember, we are dealing with a random system. It's a random system in the sense, I mean to say that whatever electrons are moving inside the conductor, they are moving rapidly at in random directions, in different directions with the different values. So if I wanted to talk about any physical quantity associated with such a kind of motion, obviously I don't have a choice, I need to go to average values only. So all these are average values. If you wanted to write expression for this tau, you can write like this also. Velocity is equal to what? Displacement by time. Okay, time is equal to displacement by velocity. What displacement here we can talk about? We can talk about mean free path. Just for your knowledge, I am giving you this data. Okay, mean free path divided by drift velocity. This gives us tau. You can just remember this. Okay. Now let us proceed with one more physical quantity. It's mobility. Mobility. Mobility, see, we keep on defining things in physics based on our requirement. If I am supposed to perform any experiment, if I am supposed to analyze any data, somewhere I'm going to realize that here it would be good if we define a particular physical quantity. Like that, you can talk about mobility here. Mobility in the sense what? Moving things, mobile charges, or mobility in the sense literature meaning is what? Mobility, it's moving, something is moving. Okay, so here charges were moving. Okay, so the motion can be influenced by what? It can be influenced by electric field intensity. Because of electric field intensity, what they are getting drift velocity, isn't it? So in terms of drift velocity and electric field intensity, we can define mobility. It is denoted with mu. It is denoted with mu, and it is defined as drift velocity per unit electric field. Drift velocity per unit electric field. Okay, so if this is the case, you can talk about its units like this. Then what will be the units? Velocity, meter per second, and electric field intensity. Electric field intensity, volt per meter, isn't it? And finally, what you will get? You will get meters goes to the numerator, and finally you will have this one. Meter square, s power 1 and v power minus 1. So meter square per second per volt. So these are the units of mobility. Already we know the expression for Vd. What is expression for Vd? E tau by m. So I'm going to replace it here. Then this mobility gets modified like this: E tau by m into E in the denominator, and this E gets cancelled. Finally, mobility can be expressed as E tau by m. And we can talk about mobility for both electrons as well as in semiconductor devices chapter we talk about holes. Of course, here also we can talk about holes. Hole in the sense what? If electron is traveling from one direction to the other direction, in the opposite direction, we say that holes will travel. Hole is in the sense what? It's a region, it's a location where absence of electron has occurred. Like if electron is moved from one place to the other place, so from wherever place the electron has moved, that place can be treated as hole. Since it is depleted with negative charge, you can call that hole as a positively charged location. Okay, so mu for electron, is equal to what? E tau by m. Okay, remember this equation. Now let us continue with further discussion. This one is a bit important in the sense questions you will see in reference material, in study material based on this relation between drift velocity and current. Relation between drift velocity and current. See, I'll imagine a situation. Let us say this is a conductor. It is connected to a battery like this. Let us imagine like that. conventional direction of current can be taken like this. Let us say the potential supplied by the battery is V, and here I'll assume that length of this conductor is L, and I will take the cross sectional area of this conductor as A. There is a need of defining all these things. You will come to know eventually when I go with the derivation. You will come to know the necessity of introducing all these parameters. Okay, so inside what happens? Electrons will be moving if this is the conventional direction taken, or if this is the field direction, electric field direction. Electrons will move in the opposite direction with a velocity equal to what? Drift velocity, isn't it? So these details are sufficient. Let us proceed. What I am trying to do? I am trying to derive a relation between drift velocity and current. What is the basic mathematical equation related to current? It's I is equal to Q by T. I is equal to Q by T, isn't it? So let us find out how much charge is flowing in a given time. Okay, I'll define one more term here. Let N is equal to number density of electrons. Number density of electrons. Number of electrons per unit volume. And here, what is the total volume of the conductor? Total volume of the conductor can be expressed as cross sectional area multiplied with length. Remember, children, we see this particular term, area multiplied, base area multiplied with the length many a times. We have already come across. Okay, you have to remember this one. If you take a cylinder, when you multiply base area with the length, what you will get? You will get volume. When you multiply circumference of the base with the length, what you will get? You will get curved surface area. You have to remember. So here, total volume of the conductor is what? A into L. So therefore, number of electrons present in the total volume is equal to how much? Per unit volume, n number of electrons are there. For this total volume AL, NAL will be number of electrons present. Therefore, total charge Q is equal to, how many number of electrons are there? NAL. Each electron's charge is how much? E. So total charge will be NAL into E. NAL into E. So now we came to know the value of Q. Let us find out what this T is. T, time taken for the flow. T is equal to, in terms of velocity it can be expressed. Velocity is equal to distance, displacement by what? Time taken, right? So here I am talking about time taken. So time taken will be displacement by velocity. So this T can be expressed as, how much is the displacement from this end to this end it can travel, right? Electrons at most, that is what displacement they can suffer. So you can replace with L divided by, with what velocity they are moving, with the drift velocity. So now I have got entire data here. Let us take it as equation number 1, this as equation number, not this one, because we don't need number, total number, we need total charge. I'll take this as equation number 2, this as equation number 3. So let us replace the Q and T values in equation number 1. Then what it gives? It gives us current, isn't it? It gives us current. Therefore, from 1, 2 and 3, what you can write? I is equal to, Q can be replaced with this one, NALE. NALE. N is number density of electrons, A is cross sectional area, L is length of the conductor, E is charge of the electron, divided by time. Time is what? L by Vd. L by V subscript D. LL gets cancelled, Vd goes to the numerator, then finally NAE Vd. This is the relation between electric current and drift velocity. And further you can make modifications, like you know the drift velocity's equation. What is the drift velocity's equation? Since Vd is equal to E tau by m, and if you replace it here, then I gets modified like this: NAE into E tau by m, or NAE square E tau by m. So that's how you can write expression for current. So this is some data connected with drift velocity. Okay, children. So this is where I will conclude this session. Okay, and in the next session I will continue with further discussion. Okay, I'll deal with whatever few other parameters are there. When current is traveling in a conductor, we need to consider few other parameters. We'll discuss about all those things. Thank you, children.